So this is lesson 2 of gases unit, and what we will focus mostly on this unit is that is known as the kinetic molecular theory, or KMT, ideal versus real gases, Avogadro's theory, and a relationship between volume, moles, number of moles, and at constant pressure and temperature. But yeah, before we start, I would like you to click on the video on the link that is here, is the egg in the bottle, and see how nice and neat it is, even something that it may seem impossible when you are dropping an egg into a bottle without breaking the egg and then taking the egg out of the bottle. Okay, so just watch this video and see the explanation and what is done in terms of and how is that related, that explanation is related to the gases laws that we have studied up to now. Now, when we talk about kinetic molecular theory, which is known as the KMT, there are some principles and assumptions that we do on that case. So what we consider as the kinetic molecular theory is that the volume occupied by intensities of gas is negligible in comparison to the volume of the gas itself. When we are talking about entities of gas, what do we have in mind is all the particles and molecules of the gas. Now, another thing that we keep in mind when we talk about KMT is that the entities of gas, molecules and particles of gas, are in a constant motion. So let's suppose that if we have a container that looks like this, and we have here molecules of gas, what is happening is that they are moving with a constant velocity until they hit either the sides of the container or they hit another molecule of the gas. So when they hit this, then what is happening during this collision, it's that known as the elastic collision, so that they will move into two different directions. So if this is going like that, then the collision that is happening between those particles of the gas or the sides of the container, it's known to be as an elastic collision, where the kinetic energy and the momentum is conserved. So now, another thing that we assume, or we have as a principle, we implement as a principle when we talk about kinetic molecular theory, is that the entities of the gas are not exerting any attractive force between each other or on the surrounding, on the container. Okay, so there is no force in between them. So the three, if we summarize the three principles of KMT, is that the volume of the gas itself is so small in comparison of the entities of the gas, of the molecules of the gas, is so small in comparison to the volume of the gas itself. And this is where we come to that condition where we consider that the volume of the molecules of the gas is almost negligible, so we don't take it into consideration. The second one is that there is no attraction between the particles or molecules of the gas, and the third one, the collision that is happening between the molecules of the gas itself and the container, is elastic collision. So now, if you take a look on page 172 and 173 of your textbook, then you will notice that there is an explanation of the ideal gases versus real gases or non-ideal gases. when we talk about ideal gases, we have in mind this KMT theory. So I will start with something here that in the ideal gases, what we consider volume of entities is 0. And here for the real gases, actually they do have a volume that we have to consider. Okay, volume of entities is not 0. So what we are saying in the ideal gases is that we can even have a volume of 0. If we have a gas and we compress it so much, then we can even have a volume of 0. Now, I would like you to stop the video here and read page 170, 172, and 173 in your textbook, and then complete this table, and you will see this table completed by me in a few seconds. So in terms of the table, you should have something like this, where on top of the volume of entities is 0 for ideal gases, for the real is not, and molecules are moving freely on an ideal gas, and they are colliding each other in an elastic collision, and they are far apart from each other, versus in the real gases, what we see is that when we have high pressure or low temperature, the motion is very limited. The motion of the particles is very limited, since they will be close to each other. And actually the collision that is happening in between the entities and with the container that the gas is at is considered to be an inelastic collision. So ideal gases they perfectly obey perfectly all the gases law, as we have explained them. All the gases law, and it doesn't matter what is the condition, high pressure or low temperature, still they will obey those laws. But we know that actually this situation is not a real situation. It's a hypothetical situation. Because we know that even though that when we have a high volume or relatively low pressure and high temperature, the molecules of the gas, yes, of course, they have a volume that is considered as close to 0. But when we have high pressure and low temperature, what is happening is that those molecules are becoming close to each other, which we have to take into the consideration the volume of the entities or the molecules of the gas. This is saying this is that we cannot compress infinitely real gas. So the real gases, on the other hand, what do they do is that they deviate from the gases law, and there will be certain conditions that we from gases law, and will be certain conditions like high pressure, low temperature, where we see that the density of the molecules of the real gases, that we have to take it into the consideration. So this is the difference between the ideal and the real gases. So we not always, the real gases not always obeys the law of gases, but when we have high pressure and low temperature, they don't. Versus the ideal gases, they obey the gases laws all of the time. So all the laws that we have mentioned in terms of the gases, laws like combined, Boyle's, Charles, Guy, Lusiak, are all for ideal conditions. We are using those laws even for real gases, but what we have to take into consideration is that we are making here a big assumption and considering that gases around us are behaving as ideal gases. Now, ideal gas law is a combination of all the ideal gases, which are Boyle's, Charles, Guy Lusiak, Guy Lusiak's law, and combined. And it is applicable for ideal conditions. The formula for ideal gas law is PV is equal to nRT, and on this formula, P stands for pressure, as always. It is measured into kilopascal. Volume is in V is volume in liters. N is the number of moles, which is dealing with the amount of gas in a container or in the process. T is temperature in Kelvin, and R is the gas constant, which is a number that you have to write it again into your data booklet, and it is 8.314 kilopascal liter kpal over mole K. Okay, so the reason that we have those units is because we need to cancel out the units in order to have an equal sign between the product of PV and NT. Okay, so let's take a look at the example that we have here. What is the volume of 3.5 moles of neon at a temperature? So number of moles is 3.35, not 3.5 moles. Temperature, we will convert it straight to the temperature in Kelvin. So temperature will be 42.5 degrees plus 273.15, and this will be whatever the calculator is giving us, so 315.65 Kelvin. And then we have a pressure of 96.5 kilopascal. So now we are looking for volume. Now what we have is PV is equal to nRT. On this relationship, another thing that we know, and it's constant, 314, you can use the units or not, but at the beginning, it's fine to use the units. So kpal over mole K. And now we are isolating for V here. So V will be equals to nRT over P. And if we substitute what is given, then we will have 3.35 mole. I will use different colors so that you can see. Times R is 8.314 kpal over mol K times T is 315.65 Kelvin. The whole thing is over the pressure that is, let's use the red here, the pressure that is 96.5 kPa. So now see the cancellation that it's done here. Moles and moles is cancelled out, and then Kelvin and Kelvin is cancelled out. So then we have kPa on the top. Then that means that kPa and kPa will cancel out. So the units will be in liters, and this is what we have. And in your calculator, we will find that the volume is 91.1 liter. So 91.1 liter, if we take into the consideration the number of sigdics, which is 3, because this is what we have here, 3, 3, 3, the lowest one is 3. Okay, so now let's move to the second example. And the second example is when we know the large quantity of chlorine is produced. One second. The chemical amount of chlorine in 170 liters of gas at 35 degrees Celsius and 400 kilopascal is, so what we are looking for is the N, okay, the number of moles, the amount of the chlorine. Now what we have on this is that pressure is 400 kilopascal, the volume is 170 liters, temperature is 35 in degrees Celsius plus 273.15, and this will be 308.15 in Kelvin. So, and we know that R is the constant, 8.314 kPa over mol K. Okay. What we are looking for is N, so we start with the ideal gas. PV is equal nRT. From here, N will be PV over RT. And if we substitute whatever we have as given here, 400 kPa times the volume is 170 liters over 8.314 kPa over mol K times the temperature that is 308.15 K. So Kelvin is cancelled, kPa is cancelled, and then liters are cancelled. 1 over 1 over mole will be moles. So the number of moles will be, using the calculator, whatever the calculator is given, considering the correct significant digit. What the calculator is giving you is 26.5, considering the correct significant digits, which the final answer should be recorded into 2 significant digits, and we can say it is equal to 27 moles. If they are asking you to find the amount in grams, the mass of this, then you will use the fact that we are dealing with chlorine gas, and chlorine gas is Cl2, and then from here you will find the molar mass of chlorine gas using the table. So for chlorine, what we have is molar mass is 2 times 35.45 grams per mole. So 2 times 35.45 will be equals to 70.9 grams per mole. And if we are finding the mass, then we will go 27 mole that we have here times this number, as we have been mentioning often, is 70.90 grams is 1 mole, or 1 mole of chlorine gas is 70.90 grams. So we will use the proper ratio to cancel the number of moles, and this will be moles, 1 mole on the denominator and 70.9 grams of chlorine gas in the numerator, and we will have 27 times 70.9 equals to 1,914.3 grams, or you can go 1.9 times 10 to the power of 3 grams, or 1.9 kilograms. So this is taking into consideration the correct number of Sigdix. Next example here is asking you what is the temperature of 6.50 grams of sulfur dioxide gas that is occupying 10 liters at 125 kilopascal. So pressure is 125 kilopascal. Volume is 10 liters. And then what we have is a mass, which is 6.50 grams of sulfur dioxide. And then we have the R constant, the gas constant, as 8.314 kPa over mole K. And we are looking for temperature. In the ideal gas law, what we have is PV is equal to nRT. From here, we find that T is equal to PV over nR. However, we have the mass, and we will calculate the number of moles for sulfur dioxide. So now let's calculate the molar mass of sulfur dioxide. So we have 1 sulfur and 2 oxygen, and 1 sulfur is 1 times 32.07 plus 2 times 16. So 32.07 plus 32 is equal to 64. Molar mass is 64.07 grams per mole. What does this number means is that if we have 1 mole of sulfur dioxide, then we have 64.07 grams of sulfur dioxide, or if we have 64.07 grams of sulfur dioxide, then we have 1 mole of sulfur dioxide. So using this information, starting with what is given, 6.50 grams will be multiplied by the first ratio here. So 1 mole over 64.07 grams. So grams and grams are cancelled out, and then we will have a value of 0.10145 and so on mole. We'll keep it for now as this number, and we'll do the rounding at the very end. So now the temperature will be E, that is 125 kilopascal, times volume, that is 10 liters, over 0.10145 and so on mole, times R, that is a constant, 8.314 kPa times liter over mole K. So the units will be cancelled out, and you will end up having only the temperature And after you enter it in your calculator, you will have a value of the temperature will be 1482 Kelvin. And if they're asking you for the degree Celsius, then you use the conversion. Let's move now to another example. What is the mass of oxygen gas sample at a volume of 29 liters that is under the pressure of 243 kilopascal, and it's held at a temperature of 43 degrees Celsius, which when we convert it to we add 273.15 into Kelvin, and then we will have 316.15 Kelvin. Then what we are asking is what is the mass? So what is M? Okay, so now we'll start always with PV is equal nRT. From here we find N as PV over RT. So in this situation, what we will have is 243. I'm not writing the units now because you get that they will be cancelled out, times 29 over 8.314 times 316.15. Using your calculator, you will have a value of N of what the calculator is giving you is something like this, moles. Now, to honor the significant digit, the lowest one is 2 degrees, so the final answer will be 2.7 moles. And if they are asking you to find the mass, then use the fact that oxygen gas has 2 atoms into its molecule and find the molar mass, and then go through the process as we did before. Now it's your time to try this. At what temperature in Kelvin does 16.3 grams of nitrogen gas with a pressure of 126.7 kilopascal in 25-liter tank is? And the answers should be those two, either in Kelvin or in degree Celsius. Okay, let's take a look now to that is known as the Avogadro's law. And the Avogadro's law states that equal volumes of gases at the same temperature and pressure will contain equal numbers of molecules. And since they contain the same equal number of molecules, then that means that we are having the same mole ratios, okay? The same moles. Okay, so in other words, this is known as the law of combining volumes. So volumes of gases, reactants and products of a reaction will always be in the simple whole ratios at a constant pressure and temperature. Okay, so this is known as the volume is in direct proportion to the number of moles at constant pressure and temperature. So this is what we have here in and this completes now all the possible combinations of PV is equal nRT, which one is constant and which one is not, and what is happening with this relationship when one or two are kept constant. So remember what we said, Boyle's law, Charles' law, and all that. We are stating that this is constant, this is constant, this is fine. That is the relationship. They all derive from PV is equal nRT. Okay, so now let's see. At constant temperature and pressure. Okay, so let's take a look now. If we have a reaction between 1 liter of nitrogen and 3 liters of, if we have hydrogen and nitrogen reacting together to produce ammonia, so this is ammonia. To produce ammonia, the reaction will be something like this. If we balance it, then we will have 3, 1, and 2. So that is telling us that if we have 3 liters of hydrogen reacting with 1 liter of nitrogen, then what we will have is we will have 2 liters of ammonia. So the volume is direct proportion to nitrogen, considering that the temperature and the pressure are kept constant. So therefore, the relative volume of the gas depends only on the molar coefficient of the reaction. Okay. So now let's take a look at this example here. What volume of carbon dioxide will be produced if 2.3 liters of methane is combusted? So now, if we write the reaction, then we will have CH4 gas plus carbon plus oxygen in combustion plus O2 will give us carbon dioxide gas, and they are all gases, okay, plus water, H2O. Now, if we balance it, then we'll add a 2 here and a 2 here. You can stop and do the balancing and then check your work. What is given here is that we will have methane. So what is given is this 2.03 liters, no, 2.30 liters of methane. Liters of methane. This is what is given, and we are asking how many, what is the volume of carbon dioxide. So now the ratio between methane and carbon dioxide is 1 to 1. Yeah. The ratio of methane and carbon dioxide is 1 to 1. So 2.30 liters of methane times the molar ratio. So 1 mole of methane is 1 mole of CO2. So meaning that is the liters will, like methane and methane will cancel out, and moles will cancel out. So what you are ending up with, since they are direct proportion of each other, what you are ending up is 2.30 liters of carbon dioxide. Okay. Now let's see now what is happening when a butane is undergoes into a combustion reaction. Let's write a balanced equation. You can check and see if it is balanced, but this is what I have, 2C4 H10 in gas state plus 13O2 gas state will produce 8 CO2 gas plus 10 H2O gas. And now, see now the coefficients are 2, I will highlight them, 2, 13, 8, and 10. Okay, so now if we have 2 moles of butane, then we will need 13 moles of oxygen, which will produce 8 moles of, those are the coefficients here, 2, 13, 8, and 10, which will produce 10 moles of water. And now if we have 16 moles of carbon dioxide, and 16 is 8 times 2, then that means that we will have 2 times 2 moles of butane. 2 times 13 is 26 moles of oxygen, and 2 times 10 is 20 moles of water. And if we have 5 moles of water, so will be 5 is 10 divided by 2, we will have 4 divided by 2 is 4, 8 divided by 2 is 4 moles of carbon dioxide, 13 divided by 2 is 6.5 moles of oxygen, and 2 divided by 2 is 1 mole of butane that is needed to produce it. Okay, now let's see now, nitrogen gas and the hydrogen the gas are combined together to form ammonia. What volume of nitrogen is required to produce 100 liters of ammonia? So we'll start with the reaction. The balanced reaction will be 3 hydrogen plus gas, okay, plus 1 nitrogen will produce 2 ammonia, NH3 gas. So the ratios are 3 to 1, even though that we don't write it, to 2. Now what it is saying, or the question is saying, what is the volume of nitrogen, so this one here, if we have 100 liters of ammonia. So now 100 liters of ammonia, NH3, times the molar ratio. So we'll take a look between the molar ratio of ammonia and nitrogen. So in order to find which one are we using, nitrogen over ammonia or ammonia over nitrogen, we have to see if we can cancel. So 1 mole of nitrogen over 1 mole of ammonia, NH3, and what is happening, this is canceling this, and moles are canceling that, and what are cancelled between each other, and then what you're ending up is volume of nitrogen, which will be 50 liters of nitrogen gas. And what we are doing here is we are again taking into the consideration the significant digits. We talked a bit about the molar volume of the gases when we explained what is the SAT and STP conditions. So what the molar volume of gas is the volume of 1 mole of gas that occupies at that occupies a specific conditions of pressure and temperature. So what is the volume of 1 mole of any gas that occupies at a specific pressure and temperature? When we are talking the STP conditions, then the molar volume is a specific number that is 22.4, and when we discuss the SATP conditions, then what we have is 24.8 liters per mole. Now, if the pressure and temperature, are not at STP or SATP condition, then the molar mass, the molar volume needs to be calculated, but using this information here. So let's see now why those two numbers, 22.4 and 24.8, are coming from. So if we have STP conditions, what we have is a pressure of 1.325 kilopascal. We have a temperature of 273.15 Kelvin, and R, that is the constant, 8.314 kPa over mole K. Okay, if we put everything into what is N, so N will be based on the information PV is equal nRT. So from here we find that N, or no, volume per liters, okay? Volume per liters, volume per N, volume per moles, sorry, volume per moles will be RT over P. Or if we use unit analysis, then we will have 8.314 kPa over mole K times 1 over 101.325 kP over 273.15 K. Then you will have 22.4 liters per mole, okay, which is the STP conditions. The same logic we will follow for SATP conditions, but what do we have to keep in mind on this case is that R is still 8.314 kPa over mole K. And pressure now is 100 kilopascal. Temperature is in Kelvin is 298.15 Kelvin because it's 25 degrees. And when we do the calculations, 8.314 over 1, and the units here, they will cancel out, but let's write them again, times 1 over 100 kPa and 298.15 K over 1, then we will have a value of 24.8 liter per mole, which is the molar mass at SATP conditions. So those numbers are not that they are something that the scientists made them up, but it is as a result of those calculations that you see here. Now, next example is asking you what is the molar volume if we have a pressure of 350 kilopascal and a temperature of 305 Kelvin. So 8.314 kPa over mole, okay, times 1 over 350 kPa. So kPa, kPa and kPa is cancelled out. And then we have a temperature of 305 K over 1. So K and K is cancelled out. And what you are ending up with is liters per mole. And when you enter this in your calculator, you will have 7.25 liters per mole. And this will be taking into the consideration the fact that the number of significant digits is 3, so this is what we do. Okay, now let's move to next question. When we are calculating the volume occupied by 0.024 moles of carbon dioxide at SATP conditions. So now at SATP conditions, what we have is 24.8 liters occupies 1 mole, or is volume occupied in SATP is of 1 mole is 24.8, or 1 mole will be 24.8 liters of any gas. Doesn't matter which gas are you talking about. So now what do we have? We start with what is given, 0.024 moles of carbon dioxide times which ratio are we using, ratio 1 or ratio 2? And we have to think which ratio are we using so that we can cancel the units. And the units of mole will be 24.8 liters of carbon dioxide over 1 mole of carbon dioxide. So moles and moles are cancelled out, and then you will end up with 0.595 liters of carbon dioxide, and this will be your final answer. Okay, so now let's move to the next example here. When we have what volume does 3.50 grams of helium occupies at SATP conditions. So first of all, we need to know the number of moles. So what is given here is the amount, but in grams. So molar mass of helium is, we find it directly at the periodic table, is 4.0 grams per mole. And as we have always mentioned, that means that if we have 4.0 grams of helium, then we have 1 mole of helium. And if we have 1 mole of helium, then we have 4.0 grams of helium. So we have 2 ratios here, ratio 1 and a ratio 2. Okay, so now we start with what is given, 3.50 grams of helium times, and we think which ratio do we have to use, 1 or 2, in order to cancel the moles that we have at the numerator, and it is a ratio 2. So we have 1 mole of helium over 4.0 grams of helium. So grams of helium and grams of helium is cancelled out. What we are ending up here is the number of moles. but we don't want this. We want the volume that it occupies at SATP conditions. And since we are dealing with SATP conditions, what we have here is that molar volume at SATP conditions is, we know, 24.8 liters in a 1 mole, or 1 mole of any gas, and in this case will be helium, is 24.8 liters of helium. So again, what we have is two ratio 1 and the ratio 2, and we have to think now which ratio are we using, 1 or 2, in order to cancel the moles so that we have on the numerator, and will be ratio 1, so 24.8 liters of helium and 1 mole of helium. So moles and moles are canceled out. And then what do you do in your calculator? 3.50 times 24.8 divide by 4, and you should have 21.7 liters of helium. And again, this is taken into the consideration the correct number of SIGDIGs. And now we have another example. Actually, I want you to try this example, and I will just tell you what is the answer. It will be 50.4 liters. It's not difficult. So what do you have is the number of moles as 2.25 moles, and you will find what is the volume. And this is the end of lesson 2. Please complete the assignments for this lesson, which will be posted.